Welcome one and all to a special podcast introducing you to the Reith Lectures, a BBC institution that's been running since 1948. Every year we open the mic to a leading figure of the day, inviting them to share their thoughts, knowledge, research and beliefs with us. The very first lecture was by Bertrand Russell, the eminent philosopher, and was titled Authority and the Individual.
The fundamental problem I propose to consider in these lectures is this. How can we combine that degree of individual initiative which is necessary for progress with the degree of social cohesion that is necessary for survival? I shall begin with the impulses in human nature that make social cooperation possible. I shall examine first the forms that these impulses...
As you can hear, from day one, the lectures haven't held back on subject and detail. I found myself having to listen to them a couple of times to fully absorb everything. For 2016, the BBC asked the revered theoretical physicist and cosmologist Professor Stephen Hawking to present 2 lectures on the subject that he has made his own, black holes. But fear not, friends, help is at hand. At the end of each lecture, there will be a Q&A from presenter Sue Lawley with the Professor, with all the questions sent in by listeners. That's when we get to hear a little more about what makes the great man tick. And if that wasn't enough, on the Radio 4 website, there's even more help with getting your head around black holes. I recommend starting with the beautiful psychedelic animation called Inside the Mind of Professor Stephen Hawking, made by Aardman Studios, no less. Also, if you want to brush up on your intellectual icebreakers, it just so happens the presenter of the Life Scientific, Jamal Khalidi, has written a piece for the Radio 4 in 4 website to help you impress with your knowledge of the second law of thermodynamics. But for now, let's set out on our journey into space and over to Sue Lawley.
Hello and welcome to the BBC Reith Lectures. We're at the Royal Institution of Great Britain in the West End of London. It was founded in 1799 to encourage people, and I quote, to think more deeply about the wonders and applications of science. Can there be a better person to fulfil that ambition than this year's lecturer? When we advertised his name on the airwaves, 20,000 listeners applied for tickets. So I'm looking at 400 lucky people gathered here in this historic lecture theatre. A little bit first about the man who commands such interest. He was a brilliant, though by his own admission, lazy physics student at Oxford in the 1960s. The course was ridiculously easy, he said. But the career which followed, like the stars he loves so much, has shone brightly ever since. Despite being diagnosed with a rare form of motor neuron disease when he was 21, and the physical deprivations it's caused, his work on the laws which govern the universe have been groundbreaking. The subject of his Reith Lectures is what else? Black holes. They've held a fascination for him for the past half-century. Virtually invisible and billions of miles away, we nevertheless regard them as menacing. A mistake, says our lecturer. If we could understand them, then we could possibly unlock the secrets of the universe. Ladies and gentlemen, please welcome the world's most famous scientist and the BBC Reith lecturer, Professor Stephen Hawking. Stephen, welcome. The last time we broadcast together, it was Christmas 1992, and it was on another BBC radio programme, and you were struggling to choose between chocolate mousse and creme brulee. Yep, it was Desert Island Discs, and that was to be your luxury. I wonder if you remember this.
Your mother has said that you always had what she described as a strong sense of wonder. I could see that the stars could draw him, she said. Do you remember that?
I remember coming home late one night from London. In those days, they turned the street lights out at midnight to save money. I saw the night sky as I had never seen it before, with the Milky Way going right across. There won't be street lights on my desert island, so I should get a good view of the stars.
Well, that was 23 years ago, and you didn't really fancy being cast away, I recall.
Can you hear me?
We can.
23 years ago, the idea of being stuck on a desert island filled me with horror. At that time, I wanted to be in the heart of the action, where things were happening, not stuck in some remote, quiet spot. Now that I am older, a desert island suddenly sounds quite appealing. I might get much more work done. But I still don't want to go if there's no creme brulee. Physics is fascinating, but after all, you can't have it for pudding.
Well, right now, physics is the main course, so serve it up if you would, Stephen. Ladies and gentlemen, lecture number 1 is entitled, Do Black Holes Have No Hair?
My talk is on black holes. It is said that fact is sometimes stranger than fiction, and nowhere is that more true than in the case of black holes. Black holes are stranger than anything dreamed up by science fiction writers, but they are firmly matters of science fact. The scientific community was slow to realize that massive stars could collapse in on themselves, under their own gravity, and how the object left behind would behave. Albert Einstein even wrote a paper in 1939 claiming stars could not collapse under gravity because matter could not be compressed beyond a certain point. Many scientists shared Einstein's gut feeling. The principal exception was the American scientist John Wheeler, who in many ways is the hero of the black hole story. In his work in the 1950s and 60s, he emphasized that many stars would eventually collapse, and the problems that posed for theoretical physics. He also foresaw many of the properties of the objects which collapsed stars become, that is, black holes. During most of the life of a normal star, over many billions of years, it will support itself against its own gravity by thermal pressure caused by nuclear processes, which convert hydrogen into helium. Eventually, however, the star will exhaust its nuclear fuel. The star will contract. In some cases, it may be able to support itself as a white dwarf star. However, Subramanian Chandrasekhar showed in 1930 that the maximum mass of a white dwarf star is about 1.4 times that of the Sun. A similar maximum mass was calculated by Soviet physicist Lev Landau for a star made entirely of neutrons. What would be the fate of those countless stars, with greater mass than a white dwarf or neutron star, when they had exhausted nuclear fuel? The problem was investigated by Robert Oppenheimer, of later atom bomb fame. In a couple of papers in 1939, with George Volkoff and Hartland Snyder, he showed that such a star could not be supported by pressure, and that if one neglected pressure, a uniform spherically systematic symmetric star would contract to a single point of infinite density. Such a point is called a singularity. All our theories of space are formulated on the assumption that space-time is smooth and nearly flat, so they break down at the singularity, where the curvature of space-time is infinite. In fact, it marks the end of time itself. That is what Einstein found so objectionable. Then the war intervened. Most scientists, including Robert Oppenheimer, switched their attention to nuclear physics, and the issue of gravitational collapse was largely forgotten. Interest in the subject revived with the discovery of distant objects, called quasars. The first quasar, 3C273, was discovered in 1963. Many other quasars were soon discovered. they were bright, despite being at great distances. Nuclear processes could not account for their energy output, because they release only a percent fraction of their rest mass as pure energy. The only alternative was gravitational energy, released by gravitational collapse. Gravitational collapses of stars were rediscovered. It was clear that a uniform spherical star would contract to a point of infinite density, a singularity. The Einstein equations can't be defined at a singularity. This means at this point of infinite density, one can't predict the future. This implies something strange could happen whenever a star collapsed. We wouldn't be affected by the breakdown of prediction if the singularities are not naked, that is, they are not shielded from the outside. When John Wheeler introduced the term black hole in 1967, it replaced the earlier name, frozen star. Wheeler's coinage emphasized that the remnants of collapsed stars are of interest in their own right, independently of how they were formed. The new name caught on quickly. It suggested something dark and mysterious, but the French, being French, saw a more risky meaning. For years, they resisted the name, true knower, claiming it was obscene. But that was a bit like trying to stand against The Weeknd, another Franklin. In the end, they had to give in. Who can resist a name that is such a winner? From the outside, you can't tell what is inside a black hole. You can throw television sets, diamond rings, or even your worst enemies into a black hole, and all the black hole will remember is the total mass and the state of rotation. John Wheeler is known for expressing this principle as, a black hole has no hair. To the French, this just confirmed their suspicions. A black hole has a boundary, called the event horizon. It is where gravity is just strong enough to drag light back and prevent it escaping. Because nothing can travel faster than light, everything else will get dragged back also. Falling through the event horizon is a bit like going over Niagara Falls in a canoe. If you are above the falls, you can get away if you paddle fast enough, but once you are over the edge, you are lost. There's no way back. As you get near the falls, the current gets faster. This means it pulls harder on the front of the canoe than the back. There's a danger that the canoe will be pulled apart. It is the same with black holes. If you fall towards a black hole feet first, gravity will pull harder on your feet than your head, because they are near the black hole. The result is, you will be stretched out longwise and squashed in sideways. If the black hole has a mass of a few times our sun, you would be torn apart and made into spaghetti before you reached the horizon. However, if you fell into a much larger black hole with a mass of 1,000,000 times the sun, you would reach the horizon without difficulty. So, if you want to explore the inside of a black hole, make sure you choose a big one. There is a black hole with a mass of about 4,000,000 times that of the sun, at the center of our Milky Way galaxy. Although you wouldn't notice anything particular as you fell into a black hole, someone watching you from a distance would never see you cross the event horizon. Instead, you would appear to slow down and hover just outside. Your image would get dimmer and dimmer, and redder, until you were effectively lost from sight. As far as the outside world is concerned, you would be lost forever. There was a dramatic advance in our understanding of these mysterious phenomena, with a mathematical discovery in 1970. This was that the surface area of the event horizon, the boundary of a black hole, has the property that it always increases when additional matter or radiation falls into the black hole. These properties suggest that there is a resemblance between the area of the event horizon of a black hole and conventional Newtonian physics, specifically the concept of entropy in thermodynamics. Entropy can be regarded as a measure of the disorder of a system, or equivalently, as a lack of knowledge of its precise state. The famous second law of thermodynamics says that entropy always increases with time. This discovery was the first hint of this crucial connection. Although there is clearly a similarity between entropy and the area of the event horizon, it was not obvious to us how the area could be identified as the entropy of a black hole itself. What would be meant by the entropy of a black hole? The crucial suggestion was made in 1972 by Jacob Bekenstein, who was a graduate student at Princeton University and then at the Hebrew University of Jerusalem. It goes like this. When a black hole is created by gravitational collapse, it rapidly settles down to a stationary state, which is characterized by only three parameters: the mass, the angular momentum, and the electric charge. Apart from these three properties, the black hole preserves no other details of the object that collapsed. His theorem has implications for information. In the cosmologist's sense of information, the idea that every particle and every force in the universe has an implicit answer to a yes-no question. The theorem implies that a large amount of information is lost in a gravitational collapse. For example, the final black hole state is independent of whether the body that collapsed was composed of matter or antimatter, or whether it was spherical or highly irregular in shape. In other words, a black hole of a given mass, angular momentum, and electric charge could have been formed by the collapse of any one of a large number of different configurations of matter. So what appears to be the same black hole could be formed by the collapse of a large number of different types of star. Indeed, if quantum effects are neglected, the number of configurations would be infinite, since the black hole could have been formed by the collapse of a cloud of an indefinitely large number of particles of indefinitely low mass. But could the number of configurations really be infinite? The uncertainty principle of quantum mechanics implies that only particles with a wavelength smaller than that of the black hole itself could form a black hole. That means the wavelength would be limited, it could not be infinite. It therefore appears that the number of configurations that could form a black hole of a given mass, angular momentum, and electric charge, although very large, may also be finite. Jacob Bekenstein suggested that from this finite number, one could interpret the entropy of a black hole. This would be a measure of the amount of information that was irretrievably lost during the collapse when a black hole was created. The apparently fatal flaw in Bekenstein's suggestion was that if a black hole has a finite entropy that is proportional to the area of its event horizon, it also ought to have a finite temperature, which would be proportional to its surface gravity. This would imply that a black hole could be in equilibrium with thermal radiation, at some temperature other than zero. Yet according to classical concepts, no such equilibrium is possible, since the black hole would absorb any thermal radiation that fell on it, but by definition would not be able to emit anything in return. It cannot emit anything, it cannot emit heat. This is a paradox. And it's one which I am going to return to in my next lecture, when I'll be exploring how black holes challenge the most basic principle about the predictability of the universe and the certainty of history. And asking what would happen if you ever got sucked into one. Thank you.
Thank you. Thank you very much indeed, Stephen. Well, now, we asked listeners what they'd like to ask you, and their questions came flooding in, hundreds of them. We've chosen a representative selection of topics and invited some of those listeners to come and put their questions in person. You'll appreciate, audience, that we had to give Stephen the questions beforehand so that he could program his answers into his computer. This is done letter by letter through the movement of his facial muscles, and you'll hear little tiny bleeps as the infrared detector picks up those movements. It's not a speedy process, round about a word a minute, but the answers are all in there now. So if you're ready, Professor, let me begin by asking Andy Fabian, who's an astronomer and astrophysicist. He's the director of the Institute of Astronomy at Cambridge and therefore a colleague of Stephen's. Andy, your question, please.
Stephen, much of the work by yourself and others on issues such as the potential loss of information in black holes and on radiation from black holes is theoretical and lacks observational support so far. Do you see ways to change that situation using the many and varied observations now routinely being made of accreting black holes throughout the cosmos?
Stephen.
I assume you are referring to the area increase law for black hole horizons. The best way of testing this is black hole collisions, rather than accretion.
Well, you got pretty short shrift there. So, perhaps you should tell us what the difference is between accreting black holes and black hole collisions.
Well, black hole collisions are when you have two black holes colliding with each other and merging together. Accretion is just matter dribbling into the black hole steadily. And it produces enormous amounts of energy release, very luminous things in the universe.
Do you foresee that there will be evidential proof of what Stephen is talking about? As you say, it's all theoretical at the moment.
It would be fantastic to find observational proof of it, but I myself don't see how to do it.
Okay, well, let's pursue this theme of what black holes get up to when we're looking at them, and indeed when we're not, and turn to a group of young enthusiasts here from the West Midlands. They're pupils from Burr Beacon Secondary School in Walsall, and they're aged around 12 or 13. Kate Harris, you're their teacher. How have you got them interested in cosmology and everything else?
Well, I'm their form tutor, so I look after them every morning. And received an email from one of the science teachers who's with us, Dr. Butterworth, about Stephen's lecture, and told them about it. And they were so keen to know more because, firstly, they've seen him in The Big Bang Theory.
This is the television, the American sitcom.
Yes, yeah, and also they are keen science enthusiasts. They just wanted to know more.
Yeah, so endlessly interested. Well, let's have a question from one of them. Arunya Moralidaran, you're age 12. What's your question?
What kind of things would happen if one black hole collided with another one?
If two black holes collide and merge to form a single black hole, the area of the event horizon around the resulting black hole is greater than the sum of the areas of the event horizons around the original black holes.
Did you understand that, Arunya? Did you get your head around it? Well, as I understand it, it's when two black holes collide, the total circumference is greater than the sum of the two parts. The whole area increases. Got it?
I got it now.
What about you? Do you want to say something?
Yeah, I did understand it.
You did?
A bit.
Well, yeah, you did. Maybe it was because I explained it to you. Now, to a rather more personal question, and we received many of them, actually. This is from a 17-year-old Radio 4 listener. His name is Duncan McKinnon. You told us, Duncan, that Stephen had been an inspiration to you. In what way?
Well, watching the film with him, it was really inspirational how he's managed to carry on with his dreams and goals.
You mean the film The Theory of Everything, which starred Eddie Redmayne, for which he won an Oscar, of course. Great film, wasn't it? OK, like to put your question?
I would like to ask you what inspires you to keep on going despite all the rough times in your life?
Stephen.
I think my work and a sense of humor have kept me going. When I turned 21, my expectations were reduced to 0. You probably know this already, because there's been a movie about it. In this situation, it was important that I came to appreciate what I did have. Although I was unfortunate to get motor neuron disease, I have been very fortunate in almost everything else. I have been lucky to work in theoretical physics at a fascinating time, and it's one of the few areas in which my disability was not a serious handicap. It's also important not to become angry, no matter how difficult life may seem, because you can lose all hope if you can't laugh at yourself and life in general.
We have here Lucy Hawking, Stephen's daughter, just towards the front there. Lucy, you have seen Stephen over the past 4 decades, if you don't mind my saying that.
That's a little personal too.
I apologise, Lucy.
Okay. It's radio, Sue. No one can
how do you... Interjection from my right. You've seen him, Lucy, weather some pretty rough times. What do you put his resilience and this determination down to?
I think he's enormously stubborn and has a very enviable wish to keep going and the ability to summon all his reserves, all his energy, all his mental focus and press them all into that goal of keeping going. But not just to keep going for the purposes of survival, but to transcend this by producing extraordinary work, writing books, giving lectures, inspiring other people with neurodegenerative and other disabilities, and being a family man, a friend, and a colleague to so many people, and keeping up with friends across the world. So I think there are lots and lots of elements there, but I do think the stubbornness, the will to live, and, like he says himself, the sense of humour, to laugh at it at the end of the day is
I
what
would
has...
bring back Einstein. He would be amazed at how much general relativity has advanced our understanding of the world.
I think that was his way of asking me to stop talking.
And there we must end. Thank you for making this a memorable event. There's a mass of science on the BBC Reith website, including Robert Oppenheimer, whom Stephen mentioned, one of the fathers of the atom bomb, the astrophysicist Martin Reith, the radio astronomer Bernard Lovell, and many more. There's an archive of recordings and transcripts going back to 1948, so do have a look. For now, our thanks to our hosts here at the Royal Institution in London, and of course, huge thanks to our Reith lecturer, Professor Stephen Hawking.
That was part 1 of Professor Stephen Hawking's Reith lectures, presented by Sue Lawley and produced by Jim Frank. In part 2, the professor proposes that black holes ain't as black as they are painted. And if you love science as much as we do, here's a suggestion for you: BBC Inside Science with Dr. Adam Rutherford, a weekly rummage through the mysteries and challenges of the ever-changing world of science. I'm Andy Brooks, also known as Testament, and you've been listening to the Reith lectures. I'll be testing you later.